This tutorial will show how a web opening may be added to a composite beam and then checked to make sure it satisfies allowable limits. This is the beam we will check. In this case, we will be checking to see if we can add an opening to a composite beam in an existing structure. The floor framing consists of a 3-inch metal deck with 3.5 inches of concrete cover for a total depth of 6.5 inches, which is supported by W14 by 22 composite beams that span 24 feet with 12 shear studs, resulting in shear studs 2 feet on center. The materials used in the building are as shown here. Even though the building was designed with an older code, we will check the web openings against the AISC 360-22 code. The opening that we wish to add is a 6-inch by 6-inch square centered 6 feet from the end of the beam and located at the middle of the beam vertically. The building has already been analyzed for the various floor loads, and a composite design was done to check the existing sections. If we go to the Display Force Diagrams command, and then right-click on the beam where the opening is to be added, selecting the governing load combination, and then scrolling to a location of 6 feet, gives us the forces at the center of the opening. We see that the shear is 12.723 kips, and the moment is 114.5114 kip feet. We will verify in a bit that these are the forces used to check whether the opening is within allowable limits. We will return to the design display. If we right-click on the member where we wish to add the opening, the interactive composite beam design and review form is displayed. Note that it is on this form that web openings may be added. Note that only beams that are designed compositely are allowed to have web openings added. Clicking the Web Openings button, the Beam Web Openings form is displayed, where the opening or openings may be located and sized. In our case, we will have only one opening, located 6 feet from the end. We set the eccentricity to 0. This means the center of the opening will be located at the center line of the beam. A positive value moves the center of the opening up that amount above the center line. Our web opening will be rectangular or square, so the circle checkbox will remain unchecked, and we will enter a length of 6 inches and a height of 6 inches. The reinforcing edit boxes will be set to 0, as we hope to not have to reinforce the opening. Before we take a closer look at some of the results displayed, let's review some of the properties of the composite floor. The W14 by 22 section has a depth of 13.7 inches, a flange thickness of 0.335 inches, a web thickness of 0.23 inches, and an area of 6.49 inches squared. At the location of the opening, subtracting out the opening material leaves a remaining area of 5.11 inches squared. The effective width of the concrete slab on each side of the beam is limited to the span divided by 8, or 3 feet to each side, for 6 feet total. The shear studs, spaced at 2 feet on center, have a diameter of 3/4 of an inch, with a cross-sectional area of 0.442 inches squared. Next, we will examine some of the values displayed in the dimensions and location checked area. A naught is the length, and H naught is the height. The opening must be proportioned such that A naught over H naught plus 6 times H naught over D is less than or equal to 6. H naught must be less than or equal to 0.7 times D, which equals 9.59 inches. A naught must be less than or equal to 1.5 times D, which equals 20.55 inches. The depth of the T section in compression is 3.85 inches. The compression T depth must be equal or greater than 0.15 times D, which equals 2.055 inches. The distance to the edge of the opening from the beam start is 6 feet minus 3 inches, or 69 inches. Next, we will take a look at how moment capacity at the opening is calculated. Previously, we displayed the shear and moment for the governing load combination. Note that these values match those shown on this form, specifically 12.723 kips for the shear and 114.5114 kip feet for the moment. We will start by calculating Q sub n, which is the shear stud capacity. In this case, Q sub n equals R sub G times R sub P times A sub SA times F sub U, where coefficients R sub G and R sub P depend upon the orientation of the deck and the number of studs in the ribs, and F sub U is the tensile strength of the studs. This gives a Q sub n equal to 21.5 kips. Next, we will determine the compression force in the concrete slab, which is the smallest of these three equations. For PC1, the area of concrete equals the B effective of the slab times the cover, so PC1 equals 856.8 kips. For PC2, since the opening is 6 feet away from the end of the beam and the studs are spaced at 2 feet on center, there will be a total of 3 studs from the beam end to the opening, which gives a total value of 64.5 kips. For PC3, the equation gives a value of 184 kips. Thus, PC2 with a value of 64.5 kips is the governing value. From here on out, we will simply refer to PC2 as PC. We can now calculate the nominal flexural strength, which for our section is as shown because there is no eccentricity. That is, the opening is centered at mid-depth of the section and E equals 0. The depth of the compression blocks in the concrete slab, A, is as shown. D1, the distance from the compression force centroid in the slab to the top of the steel section, is as shown. Next, we will calculate D2, the distance from the compression force in the steel section to the top of the steel section. If the quantity PC plus 2 times F sub Y A sub F, where A sub F is the flange area, is greater than F sub Y times the net area, the plastic neutral axis is located in the flange. For our model, this is the case, as PC plus 2 times F sub Y A sub F equals 185.1, while F sub Y times the net area equals 184. The plastic neutral axis is located at a distance x from the top of the flange, as shown, which works out to be 0.332 inches. Thus, the distance from the centroid of the compression force to the top of the flange, or D2, is equal to x divided by 2, or 0.166 inches. The last term needed before we can solve for the nominal moment is D3, which is simply the depth of the steel section divided by 2, which is 6.85 inches. Plugging all of the values back into the nominal moment equation, we get a value of 1651 kip inches. Applying a feed factor and converting to kip feet, we get a value of 117 kip feet, which matches the value shown. Based on the capacities calculated, the end result is that the web opening may be added to the beam without any reinforcing, as indicated by the ratios displayed. This concludes this tutorial on the design checks available for web openings in composite beams.